Welcome to Unit 3, Applications of Differentiability, Calculus AB, Part 1. What is the process for solving related rates problems? Identify the variables. 2. Find an equation relating them. 3. Differentiate the equation implicitly with respect to time. 4. Substitute known values. 5. Solve for the unknown rate. Take your time when solving related rates problems. Part 2. How do you know if a given quantity is a derivative or not? If the quantity represents the rate of change of another quantity with respect to some variable, typically space or time, it is a derivative. If the unit is something over something, it is most likely a derivative. Part 3. What are units used for length? Area, volume. Some units for length include centimeters, meters, kilometers, feet, and yards. Some units for area include centimeters squared, meters squared, kilometers squared, feet squared, and yards squared. Some units for volume include centimeters cubed, meters cubed, kilometers cubed, feet cubed, and yards cubed. Remember that it is important to consider the unit when considering if a quantity is a derivative of something else. Part 4. What is extrema? What is an absolute maximum and absolute minimum? Extrema is the maximum or minimum values of a function. The absolute maximum is the highest value or point of a function within its entire domain or range. The absolute minimum is the lowest value or point of a function within its entire domain or range. Part 5. What is the extreme value theorem? The extreme value theorem states that if a function is continuous on a closed interval from a to b, then the function has both a maximum and minimum value on that interval from a to b. Here's some examples of functions where this applies because the functions are continuous. Here's some examples of functions where this does not apply because the functions are not continuous. Part 6. What is a relative maximum? What is a relative minimum? A relative maximum is a point on the graph where the function's value is greater than all nearby points, but not necessarily the highest value in the entire domain. A relative minimum is a point on the graph where the function's value is lower than all nearby points, but not necessarily the lowest value in the entire domain. Here is a graph with a relative max and relative min that are not the lowest and highest points in the function's domain. Part 7. What is a critical number? How do you find them? A critical number is an x value in the domain of f, where the derivative of f is either equal to 0 or undefined. To find the critical numbers of a function, follow these steps. First, find the derivative. Then set the derivative equal to 0 and solve the resulting equation for x. The values of x that satisfy the equation are potential critical numbers. Also, find values of x where the derivative is undefined. These are also potential critical numbers. All of these x values together are the critical numbers of a function. Part 8. Do all critical numbers result in extrema? No, not all critical numbers result in extrema. While it's true that some critical numbers result in extrema, others result in saddle points and points of inflection. Part 9. How do you find an absolute maximum and minimum on a given interval from a to b? First, find the critical points of the function. Let's say the critical points are points c and d. These are the points where the derivative is equal to 0 or is undefined. Then evaluate the function at these critical points, c and d, and at their end points, a and b. Compare the values to identify the largest value if you're trying to find the maximum, and the smallest value if you're trying to find the minimum. A common mistake that calc students make is forgetting to evaluate the endpoints. Endpoints can be larger or smaller than the maximums and minimums, but not necessarily be extrema. Always evaluate the endpoints. Part 10. What is the mean value theorem? The mean value theorem states that if a function is continuous on the closed interval from a to b and is differentiable on the open interval a to b, then there exists a point c within the interval from a to b, such that f prime of c is equal to the function's average rate of change over that interval. In other words, there exists a point c where the instantaneous rate of change is equal to the average rate of change. Graphically, this point would be where the slope of the secant and tangent lines are the same. Part 11. What is a simple relationship between the original function and the first derivative of that function? How is the concavity of a function related to the second derivative? When f of x is increasing, f prime of x is positive. When f of x is decreasing, f prime of x is negative. This is always true of a function and its derivative. If the sign of the second derivative is positive, the original function is concave up. If the sign of the second derivative is negative, the original function is concave down. If the second derivative is 0 or undefined at a point, this is a possible location for a point of inflection. This is always true of a function and its second derivative. Part 12. How can you determine where a function is increasing or decreasing using calculus? First, find the first derivative of the function you are considering. Then, identify the critical points of that function. These are the points where the derivative equals 0 or is undefined. Then analyze the sign of the derivative in the intervals between these points. A helpful tool to do this is a sign chart. Remember that when the derivative is positive, the original function is increasing, and when the derivative is negative, the original function is decreasing. Part 13. How do you find the relative extrema using the first derivative test? First, identify the critical points where the derivative is 0 or undefined. Then analyze the sign of the derivative around these points to determine if the function changes from increasing to decreasing or decreasing to increasing. Remember, when the derivative is positive, the function is increasing. When the derivative is negative, the function is decreasing. If the function changes from increasing to decreasing, this is a relative maximum. If the function changes from decreasing to increasing, this is a relative minimum. Part 14. How do you find intervals of concavity? First, determine the first derivative and its zeros. Then, determine the second derivative of the function you are considering. Lastly, test intervals between those critical points to see if the second derivative is positive or negative. If the second derivative is positive on an interval, the function is concave up on that interval. If the second derivative is negative on an interval, the function is concave down on that interval. If the second derivative is 0, like it was here, the second derivative test was inconclusive. Try the first derivative test. Part 15. What is a point of inflection and how do you find them? A point of inflection is a point on a curve where the concavity changes from up to down or down to up. To find points of inflection, you need to find the second derivative of the function you're considering, set it to 0. Find the critical numbers where the second derivative equals 0 or is undefined. Then check if the sign changes on intervals between critical numbers. If it does, then you have points of inflection where it changes. If the sign does not change, these points are referred to as points of undulation. Part 16. How do you find relative extrema using the second derivative test? First, find the critical numbers where the derivative of the function you're considering is equal to 0. Note that this is where the first derivative equals 0, not the second. Then evaluate the second derivative and plug in each critical number into this equation. Now it's time to apply the second derivative test. If the second derivative of a point is greater than 0, positive, then the original function is concave up. and this point is a relative minimum. Therefore, at -1, the function is concave up. If the second derivative of a point is less than 0, negative, then the original function is concave down, and this point is relative maximum. Therefore, at 1, the function is concave down. If the second derivative of a point is equal to 0, the test is inconclusive. This means that you need to try the first derivative test. Part 17. What are some examples of indeterminate forms? Some examples of indeterminate forms include 0 over 0, infinity over infinity, 0 times infinity, infinity minus infinity, 0 to the 0 power, infinity to the power of 0 power, and 1 to the infinity power. Part 18. What is L'Hopital's rule, and when is it used? Whenever direct substitution of a limit yields the specific indeterminate forms of 0 over 0 or infinity over infinity, L'Hopital's rule can be applied. To use L'Hopital's rule, take the derivative of the numerator and denominator and substitute the value x approaches again. If this evaluates to 0 over 0 or infinity over infinity again, L'Hopital's rule can be applied again. Sometimes you have to use it more than once. Part 19. How do you find vertical and horizontal asymptotes of a function? To find vertical asymptotes, you need to find where the function is undefined. The function is undefined when the denominator equals 0, but the numerator is some non-zero number. To find horizontal asymptotes, you need to analyze the behavior of the function you're considering as x approaches positive or negative infinity. This is done by evaluating the limit of the function as x approaches infinity and as x approaches negative infinity. If the limit approaches a constant value, that value is the horizontal asymptote. Part 20. How do you find x and y intercepts of a function? For x-intercepts, set the function equal to 0 so that y equals 0. This will give you x-intercepts because x-intercepts are simply the x value of the function when y equals 0. For y-intercepts, set x equal to 0. This will give you y-intercepts because y-intercepts are simply the y value of the function when x equals 0. Part 21. How do you find relative extrema? First, find the critical points of the function you're considering by setting the first derivative equal to 0. Then, analyze the sign around those points using a sign chart. Using this sign chart, you can determine if there are maxima, minima, or neither using the following rules. When f of x is increasing, f prime of x is positive. When f of x is decreasing, f prime of x is negative. If the function changes from increasing to decreasing, this is a relative maximum. If the function changes from decreasing to increasing, this is a relative minimum. Part 22. What are optimization problems and what is the typical process for solving them? Optimization problems are mathematical problems, where the goal is to find the best solution from a set of possible solutions, while adhering to certain constraints or limitations. This is either a maximum or minimum value of a function. The process to solving optimization problems is this. First, identify what is to be maximized or minimized and the constraints. Then draw a diagram and label it. After that, decide variables and units of measure. Write formulas and identify the domain. Find critical points. And lastly, provide a meaningful solution with units. Make sure to include the units. Take your time when solving optimization problems. Part 23. How do you know if a linear approximation is an over or under approximation? To find out if an approximation is an over or under estimate, you have to analyze the concavity of the function around the point of tangency. If the function is concave up, the approximation is an underestimate. If the function is concave down, the approximation is an overestimate. Part 24. What is linear approximation? And how can you use tangent lines to approximate a function's value at a specific point. Firstly, linear approximation uses the tangent line of a function at a specific point to estimate the function's value near that point. The equation of the tangent line is often referred to as the linearization of the function at that point. To use this method of approximation, choose a point, a f of a, to act as your point of tangency. Take the derivative of the function, then evaluate it at x equals a. Then use this formula, L of x equals f of a plus f prime of a times x minus a. Do you notice anything about this formula? This formula is the point-slope form equation rearranged. F prime of a is the same as the slope, the term m. Choose a value x near a to plug into this equation, and you will get an approximation. The closer x is to a, the closer the approximation. Part 25. What is a differential? How do you find it? A differential represents a very small change in a variable, kind of like a zoomed-in version of how quantities change. To find a differential, you start with the derivative of a function. Then multiply by dx on both sides. The result is the differential, an expression that tells you how a small change in x affects y. Part 26. How do you find the propagated error using differentials? To find the propagated error, or the propagation of uncertainty, you approximate the change in a function's output, delta y, caused by a small change in the input, delta x, using the derivative. dy equals f prime of x times dx. Let's use the example. Y equals x squared. X equals 5. Dx equals 0.1. When you take the derivative of the function, you get dy over dx equals 2x. Multiply dx on both sides and plug in the values you already have. dy equals 1. This means that if x is off by 0.1, y will be off by 1. This is the propagated error. Part 27. How do you find percent error using differentials? First, identify the function and its derivative. Then calculate the differential of the function. The relative error is the differential divided by the original value. Express this value as a percentage. Let's use the example. V equals s cubed. Take the derivative, you get dv over ds equals 3s squared. Multiply each side by ds. Now divide this new equation by the original equation. Multiply this value, 3ds over s by 100. This value, as a percentage, is the percent error. The percentage error formula is f prime of x dx over f of x times 100%. That wraps up Unit 3, Applications of Differentiability for AP Calculus AB. We covered related rates, optimization, concavity, linear approximation, and error. Everything you need to crush this unit. If this helped you out, make sure to like the video, leave a comment with any questions, and subscribe so you don't miss the rest of the series. You're building real calculus confidence. Keep going, and I'll see you in the next unit.